Hello guys, welcome to H2O, the A to Z of chemistry. I'm Dr. RITU, JOHAR, your educator for this course on chemical bonding, and I hope you are enjoying this course with me. Today going to begin with lecture 40 from the course, but make sure you watch the previous ones before doing this one. The last two lectures we have been discussing on back bonding, and today is going to be back bonding lecture number 3. In lecture number 1, we discussed what is back bonding with the help of the example of the BF3 molecule. And then we started the discussion, a detailed discussion on back bonding, many examples and applications. Last lecture, we saw if fluorine is the donor, which are the molecules which show back bonding, and what are the various related questions which can come in the examination. So we are going to continue that discussion further, and today what we are going to discuss, we are going to see nitrogen as the donor atom, we are going to see carbon as the donor atom, we are going to see various halogen atoms as the donor atoms and the related questions which can come in the examination. So again, it is going to be a very important lecture. You all have an understanding all that we have discussed in the previous lecture. Well, they are very important questions, and if you have already had a look at them, well, they are going to give you straightforward focus for each question that is going to come in the examination. So very important, please do not miss anything. Watch the lecture till the end and watch the previous lectures as well if you've just started with this lecture. It is going to be very important that you watch all the 3 lectures of back bonding to have a complete understanding of the concept. And as far as chemical bonding is concerned, well, you are supposed to watch it from the start so that you have a complete understanding of chemical bonding. We are on to 40th lecture, which means that we have made a detailed course for you people so that you have a thorough understanding of each and every concept and you do awesomely well in your examination. So let us begin with the learning today. So now you have done back bonding with oxygen and fluorine as the donor atoms in the last lecture. So we will be continuing the discussion further. We will be talking about back bonding with nitrogen as the donor atom to be the first donor today. Alright, and what you have learned in the previous 2 lectures is that back bonding is going to be between 2 atoms. One of the atom is going to have a lone pair of electrons and the other atom, this should have vacant orbitals, and between them there should be first of all a sigma bond already present, and then this is going to be a coordinate pi bond between the 2 atoms, and the necessary condition is going to be that the atom, one of them, it is going to be a second period element, and the second element, well, that should be a second or a third period element. So the first molecule that we will be discussing is NCl3, and in NCl3 you know that nitrogen, this is a second period element, and chlorine, this is a third period element. So this condition, this gets satisfied. And as far as the electrons they are concerned, so nitrogen, this has the electronic configuration outer shell, this is going to be 2s2 2p3, so this has a lone pair of electrons, and chlorine, this has the electronic configuration of 3s2 3p5, so it has vacant d orbitals, so there is a possibility of back bonding in NCl3. Alright, so what we see as the structure is between nitrogen and chlorine, we see that there are going to be 3 sigma bonds formed, one nitrogen sharing its 3 electrons equally with the 3 chlorine atoms, resulting in the formation of the sigma bonds. After that, nitrogen has a lone pair of electron and chlorine, this has vacant d orbitals, right? And these, they can form a pi coordinate bond by the sharing of the lone pair with the chlorine atom. Now, one very important thing over here that you have to remember is that this back bond, which is formed between nitrogen and chlorine, well, this is going to be a very weak bond because nitrogen has one lone pair of electrons and there are 3 chlorine atoms which want that, right? So it is nitrogen sharing its one lone pair of electrons with 3 chlorine atoms, and then this is going to be an equal distribution between all the 3. Well, this is not going to be a very strong back bond that is going to be present over here. Alright, so essentially what we can say is that nitrogen, which has forming 3 sigma bonds and one lone pair of electrons, this would have been a sp3 hybridization. What would have been the geometry? Well, it would have been a geometric tetrahedral geometry, but it is going to be distorted because of the presence of a lone pair of electrons, and it is going to be a pyramidal shape. So much is not going to get distorted over here because of the presence of the back bond, because the back bond is not a very strong bond. All right. So now if we compare the bond angles of NCl3, NH3 and NF3, we find that the bond angle of NCl3, this is 107 degrees 45 minutes. NH3 it is 107 degrees and NF3 it is 102 degrees. So here what you know is that NH3, this is again having nitrogen with one lone pair of electrons and 3 sigma bonds with hydrogens. This is a deviation from the normal or sigma bond of methane, a bond angle of 109.5 degrees to 107 degrees because of the presence of a lone pair of electrons. Right? When we compare NH3 with NF3, this we did in the last lecture also, that fluorine, this is more electronegative than nitrogen. So it is going to pull the shared pair of electrons towards itself, decreasing the electron density on nitrogen, and hence the bonded pair of electrons, they can come closer to one another because there is going to be a less bond pair repulsion. Alright. Now comparing NCl3 with NH3 and NF3, what are we seeing is that the bond angle, this is slightly greater than NH3. The slight greater value than NH3, this is because of the slight back bonding which is present in the NCl3 molecule. Alright, so the extent of back bonding is very slight because only one electron pair is distributed over 3 chlorine atoms. And what is the nature of this back bonding? Well, this is going to be again a pi d pi back bonding. Alright, so do remember all of this very importantly, that there is not going to be much back bonding strength in the NCl3 molecule. It is essentially going to be a pyramidal structure only. So the next we discuss is the molecule borazole or borazine with the molecular formula B3N3H6, and this is famously called as inorganic benzene because this has a structure similar to that of benzene. This is something that I told you while we were discussing in the previous lecture, back bonding with oxygen as the donor atom, where we were discussing B3O6 3 negative. So this is a molecule which is very important when you're going to start with the discussion separately of the groups. So where we will be discussing group 13 as one of the P block elements, where we will again be discussing about this inorganic benzene or the borazine molecule. This is very important. Okay, so why not let us understand it over here only, and then it is going to be a repetition once we start with the discussion of the separate groups. So this is going to become a very good concept in your mind. All right. So here we have boron and nitrogen showing back bonding, and if we look at the electronic configuration for the two, well, boron in the ground state, it is going to be 2s2 2p1. You have all seen this in the previous lecture. Very importantly, we have discussed so much about boron in the previous lecture. In the excited state, it is going to be 3 half-filled orbitals which are going to participate in the formation of sigma bonds. After that, there is going to be still one unhybridized p orbital left, which can accept a lone pair of electrons from nitrogen, which has the electronic configuration of 2s2 2px1 2py1 2pz1. So there is a lone pair of electrons present in nitrogen, which it can share with the empty orbital of boron, leading to the formation of a back bond. So if we look at the structure of the molecule, then what we find is that boron alternating with nitrogen, it forms a ring, and each of the boron and nitrogen atoms, this is forming a sigma bond with one hydrogen atom. All right. So here, first of all, what you can see is that each boron, this is making 3 sigma bonds, 2 with the nitrogens and 1 with hydrogen. It is going to be sp2 hybridized. Similarly, one nitrogen, this is making 2 sigma bonds with boron and 1 with hydrogen. So both of them, they are going to be sp2 hybridized. Alright, and after this, Nitrogen, this has a lone pair of electrons. Boron has an empty orbital. So each nitrogen, this is going to donate a lone pair of electrons to one boron atom, having an empty p orbital, making a coordinate bond. And this is going to be a pi coordinate bond because already one sigma bond is present between boron and nitrogen. So this is going to be an example of back bonding. So now what you can see is that between boron and nitrogen there is a double bond, then a sigma bond, a double bond, a sigma bond, a double bond, a sigma bond. So this structure, this is very much similar to the structure of benzene, where instead of the boron and nitrogen atoms we will be having carbon atoms. So benzene, this has the molecular formula C6H6, 6 carbons in the ring forming alternate double bond and sigma bond, and now we have boron and nitrogen replacing the 6 atoms of benzene, again alternate double bond and sigma bonds. So the total number of electrons in borazine and benzene, this remains the same, and because it is isoelectronic with benzene, well, this has a aromatic electron cloud. It is this two are the resonating structures. Well, there is a double bond between boron and nitrogen over here, and in this one it is a double bond over here. So essentially what we see is that this is going to be a pi electron cloud which is going to be spread over the whole ring. How do we come to know of it? Well, we come to know it from the data that we have. So this is the ring that looks like. We have two different types of atoms in the ring instead of the carbon atoms in the case of benzene. And as I was telling you about the data, how do we come to know that the whole pi electron cloud, this is delocalized over the ring? Well, we have the 6 BN bonds, first of all of them to be equal in length. They are 1.436 Armstrong. If we look at the carbon-carbon bonds in benzene, it is going to be shorter. It will be 1.397 Armstrong, but all of them, they will also be equal. Alright, and the boron-nitrogen bond length, this is in between that of a single bond and of a double bond between boron and nitrogen. A boron-nitrogen single bond is 0.15 nanometer, whereas the boron-nitrogen double bond, this is 0.131 nanometer, and this is going to be a value in between both of them. So what this suggests is that there is a partial delocalization of the nitrogen pair electrons over the whole of the ring. So this is going to be an aromatic molecule. This is going to be a planar structure just like that we have for benzene. Now let us quickly tabulate the differences between borazine, that is inorganic benzene, and benzene so that you can appreciate them and remember them that they are essentially having similar structures, but there are going to be some differences in the two molecules. So borazine, if we say, is the alternate double bond and single bond. So a single bond, boron nitrogen single bond, this has a bond length of 1.51 Armstrong, and a double bond, this should be having a bond length of 1.31 Armstrong. What we find is that all these, they are of the equal bond length, that is 1.44 Armstrong. Similarly, in case of the benzene molecule, if it is a carbon-carbon single bond, the bond length value is 1.54 Armstrong. If it is a double bond, it is 1.34 Armstrong. But what we find is that all these carbon-carbon bonds, well, they are having an equal bond length, which is 1.39 Armstrong. The angles, if we look at the nitrogen, what we find, this is nitrogen. So the angle which we find over here, this is 122.9 degrees. Whereas at boron, the bond angle, this is 117.1 degrees. Okay. In case of benzene, well, it is all carbon-carbon bonds. So it is a regular hexagon, and the angle value, this comes up to 120 degrees. And the next difference what you can see in case of borazine and benzene is that we have boron and nitrogen to be different elements. They are having different electronegativity values. This makes the electron cloud partially localized, whereas in case of the benzene ring, what we have is that all the atoms which are forming the ring, they are carbon atoms. So there is no electronegativity difference between the atoms forming the ring. Therefore, the electron cloud, this is completely delocalized over the ring. Alright, in case of borazine, it is partially delocalized, whereas in case of benzene, this is going to be completely delocalized. The next, again, we have boron and nitrogen to be different elements. So this is going to be difference in electronegativity and hence polar species, whereas benzene, it is made up of carbon in the ring and hydrogen. So these are going to be non-polar species. The borazine molecule, this is much more reactive than the benzene molecule. This undergoes generally addition reactions, whereas benzene being relatively unreactive molecule, this undergoes substitution reactions. So now let us look at a few applications of nitrogen as the donor atom, because you have a fair understanding of back bonding now. So the first one which we discuss is that we have trimethylamine CH3 thrice N, which is pyramidal in shape, whereas triethylamine SiH3 thrice N, this is a planar molecule, and you have to tell obviously why this is happening so. So first of all, let us look at the structures. This one is trimethylamine and this is triethylamine. If you look at trimethylamine, nitrogen, this has one lone pair of electrons. It is making 3 sigma bonds with 3 carbons of the methyl group. So the hybridization for nitrogen is going to be sp3. The geometry is going to be a distorted tetrahedral geometry, because the lone pair bond pair repulsion is going to be more than the bond pair repulsion. The bonded pair of electrons, they are going to come closer to one another, and the shape is going to be a pyramidal shape. This is just similar to the NH3 molecule that you have studied in the previous lectures, right? Now, if you look at triethylamine, we have again a nitrogen which has a lone pair of electrons. It is again making 3 sigma bonds with silicon. So this should also have a sp3 hybridization, but again, look back at the atoms. Nitrogen is a second period element. It has a lone pair of electrons. Silicon, this is a third period element. It has vacant d orbitals. They can share the lone pair of nitrogen and form a pi-coordinate bond, that is a back bond. So the lone pair is no longer going to be available to nitrogen, and the hybridization is going to change from sp3 to sp2. And when it is sp2 hybridization, the molecule will be a planar molecule, right? So I hope this is clear. So we have trimethylamine having no back bonding, triethylamine having a 2p pi 3d pi back bonding, which makes it a planar molecule. So this is how it is going to look like. All the 3 bonds, they are going to have a partial double bond character. And the nitrogen atom, this will be forced to adopt a sp2 hybridization. Now the next one we have is SiH3p. So this is going to be triethyl phosphine. PH3 is called as phosphine, and if we remove the hydrogen and replace them by the silyl group, it is going to be triethyl phosphine. So triethyl phosphine, this is pyramidal, whereas trigermylamine, this is again a planar molecule, right? So GIH3, this is going to be a germyl group, and this is a silyl group. PH3 is phosphine. So triethyl phosphine, and this is going to be trigermylamine. So again, if you look at these molecules, what you will be finding is that phosphorus is a third period element, silicon is a third period element. There is going to be no back bonding between them, alright. And if you look at germanium and nitrogen, nitrogen is a second period element, germanium is a fourth period element. There is going to be a 2p pi 4d pi back bonding between them. Generally, we say that this back bonding, this is not as strong as a 2p pi back bonding, or a 2p pi 3p pi, or a 2p pi 3d pi. But when this is a molecule where we see a significant back bonding, that is going to be a 2p pi 4d pi back bonding. So this is something that you should remember, that in trigermylamine we see some back bonding which is significant, and this makes the molecule planar. It is going to be again that germanium and nitrogen, they are going to participate in back bonding, right? And germanium atom, well, this is going to participate, and therefore nitrogen will be again forced to adopt a sp2 hybridization. Alright, it is not going to be sp3 for the nitrogen. It is going to share the lone pair with germanium, and hence it will be sp2 hybridization. In case of tricylyl phosphine, the internuclear distance is going to be large because phosphorus and silicon atoms, they are going to be larger atoms. Phosphorus atom also has its own vacant d orbitals. Hence, the tendency to donate the lone pair of electrons, this is going to be very less, and therefore it is going to adopt a pyramidal shape. So now you can understand why essentially we say that one of the atoms, it has to be a second period element, because it is going to be very small. Okay, and the other can be a second or a third period element, but beyond that, when the sizes, they are going to increase, so the back bonding is not going to be that very effective. So similarly, there is one more question which can be asked related to these molecules. We have the comparison of the basicity of trimethylamine and tricylylamine. Okay, and what we find is that trimethylamine, this is going to be more basic than tricylylamine, and again the answer is obviously going to be back bonding. So what you see is that these are the two molecules that we have, and in CH3 thrice N trimethylamine, there is going to be no back bonding, whereas in tricylylamine there is going to be back bonding. And when there is going to be back bonding, what does that mean? Back bonding means that the lone pair of electrons, this is not going to be available for donating to other atoms or molecules. So this is going to make tricylylamine less basic. Okay, and whereas CH3 thrice N, the nitrogen, the lone pair is easily available for donating to other atoms or molecules, and hence this is going to be more basic. So what you can look at is the difference of these two in reacting with hydrochloric acid. When there is going to be a reaction of trimethylamine with HCl, and adduct is going to be formed, there is going to be a complex formation between the two molecules, a CH3 thrice NH4 positive Cl negative. So this is a Lewis acid base adduct. Alright. Whereas when we see a reaction between tricylylamine and HCl, ammonium chloride and SiH3Cl, this is going to be formed, and this is not a complex that is being formed. Okay, and this complex is not being formed because we have this not to be a basic molecule. Okay, I hope this is clear. Let's take another application. We have methyl isothiocyanate and silyl isothiocyanate. So the isothiocyanate group, this is the NCS group. Okay, and we have first of all methyl isothiocyanate CH3NCS, and then we have SiH3NCS. So this is going to be silyl isothiocyanate. The methyl isothiocyanate, this is a bent molecule, whereas silyl, this is linear Y. So again, let us look at the structures first of all for these two molecules. Here, what you will be seeing is that in methyl isothiocyanate, it is just like a tongue twister. So we have nitrogen making a sigma bond with the carbon of the methyl group and a double bond with the carbon on the other side. And there is going to be one lone pair of electron on this nitrogen. So what is going to be the hybridization for this nitrogen? It is going to be sp2. Two sigma bonds, one lone pair of electrons. Fine. What this is going to be? This is going to be sp2 hybridization. The molecule is going to become a planar molecule, and the angle, this what we find out is this is around 142 degrees. So this is going to be a bent molecule. Now, other side, if you look at silyl isothiocyanate, we have nitrogen again making a double bond, again making a single bond with silicon, again a lone pair of electron, but this time silicon has vacant d orbitals which carbon did not have. Okay, so here this carbon, this is sp3 hybridized carbon, and it is making 4 bonds. So this means it is going to be in this excited state with no empty orbitals. So we do not see any back bonding present in the case of methyl isothiocyanate, but in case of silyl isothiocyanate, well, the back bonding is going to be present between nitrogen and silicon. So what about the hybridization of this nitrogen now? It is going to make a double bond on both sides.
A double bond on both sides lone pair is utilized in that back bonding. Well, the hybridization is now going to be sp hybridization, and sp hybridization means a linear structure. All right, so because of a high back bonding, that is going to be a 2p pi 3d pi back bonding in silyl isothiocyanate, we see that the silicon nitrogen carbon sulfur skeleton, this becomes linear one, right? So nitrogen is also making a double bond, carbon is further making a double bond, so this is going to be a linear structure. Okay, I hope this is clear. Now there is one more thing which is not related to back bonding, but I am not teaching you back bonding alone. I want you to be perfect in all the concepts. So there is one more thing which I want to add up over here about methyl isothiocyanate. Just now what we said is that nitrogen, this is sp2 hybridized. For sp2 hybridization, if there is no lone pair, what is the angle? Well, that is 120 degrees. And if it is a lone pair present, well, the bonded pair of electrons, they must come closer to one another, and the angle, this should be less than 120. What we are saying is this is greater than 120. So how do we explain this? This is something that can come to you in the examination. So here, well, the answer is going to be not back bonding, but it is going to be resonance. This structure, this has two more resonating structures. Okay. So this is one resonating structure, and this is the other resonating structure for this molecule. These are the two other resonating structures for this molecule, and over here in this one it is going to be sp hybridization for nitrogen, and here nitrogen is going to make only sigma bonds. So what we will be having is sp3 hybridization. So because of a cumulative effect of all the three resonating structures, what we find is that the bond angle, this becomes 142 degrees. So this is something that you have to remember, that this is because of resonance that we have such an angle for methyl isothiocyanate. So similar is the case with if you are given a question, that is that you have to compare the shapes of methyl isocyanate and silyl isocyanate, that is going to be CH3NCO and SiH3NCO. So NCO group, this is going to be isocyanate group. Okay. So here also the answer is going to be exactly the same. Methyl isocyanate, this is not going to show back bonding, whereas silyl isocyanate, this is going to show back bonding. Let us see one more application. We have germyl isocyanate and we have silyl isocyanate. Okay, SiH3NCO and GeH3NCO. So this is going to be germyl isocyanate. This one we've already done, so I hope I do not have to tell you. As far as germyl isocyanate group, now this is going to be concerned is that this is bend shape because of a 2p pi 4d pi back bonding, which is going to be relatively ineffective. Okay, so here we have in the last example where you saw germanium, we said that it is going to have a 2p pi 4p pi back bonding, and because of that it is going to be a planar molecule. We are going to just now compare that also, but that is going to be one exception that you have to remember, where there is a 2p pi 4d pi back bonding, which is a good one. Okay, so here what you see is that germanium and nitrogen, they are going to participate in back bonding, which is going to be a 2p pi 4d pi, but it is going to be relatively ineffective, and hence this one is not going to be able to stretch itself up to 180 degrees. It is going to open up slightly, but the back bonding is not that very good as we have it for silyl isocyanate. So this is going to be linear, this is not going to be linear, it is going to be a bent molecule. This is the application which I was just now referring to you, that we have trisilylamine and germyl amine both to be planar, whereas silyl isocyanate is linear and germyl isocyanate is bent. So first of all, let us look back again once at these two molecules. So here in first of all, trisilyl amine, we have nitrogen making 3 sigma bonds. It had one lone pair of electrons. Okay, and silicon, this had vacant d orbitals, so this participated in back bonding. So back bonding, it means that nitrogen, this is sp2 hybridized. sp2 hybridization means that this is making 3 sigma bonds. The molecule is planar and the angles, they are going to be now 120 degrees, okay, or nearly 120 degrees. So this is what we have as the structure for trisilyl amine. This is going to be a 2p pi 3d pi back bonding. If you look at now trigermyl amine, again what you see is that nitrogen, this is a second period element with a lone pair of electrons, and germanium, well, this is going to have 4d vacant orbitals now, and here this participates in back bonding with nitrogen. Okay, the extent of the back bonding, we can say that it is not strong, but yet it is strong enough to involve the lone pair of electrons of nitrogen with back bonding, and hence what we see is that this nitrogen is also going to be sp2 hybridized. The shape of the molecule is going to be a planar molecule. So here what you have to remember is that the back bonding is enough for the molecule to increase the bond angle from 109 degree 28 minutes to 120 degrees from a sp3 to sp2 hybridization for nitrogen. But in case now you look at the next molecule, this is silyl isocyanate. So here nitrogen, this is going to be involved in back bonding. So this is going to be sp nitrogen and this is going to be a linear structure. But when we move on to germanium, again this is going to be what? Nitrogen and germanium. So this one. So nitrogen and germanium, what will be the nature of the back bonding? It is going to be a 2p pi 4d pi back bonding. And if we want now this molecule to move from a sp2 to a sp hybridization, right? Only if it is going to be sp hybridization, it is going to be a linear structure. So here the bond angle, well, this has to move from 120 to 180 degree. For a 2p pi 4d pi back bonding, well, this is a large angle which has to be moved. This is not a very strong back bonding for germanium nitrogen, that the angle can shift from 120 to 180. It was possible from 109 degrees to 120 degree, but not from 120 to 180. So here what we will be seeing is that back bonding is taking place and effect of the back bonding is there, whereas in case of germyl isocyanate, we do not see the effect of back bonding to be that pronounced, and the shape of the molecule, this remains planar only. Okay, so it is going to be bend shape only. I hope this is clear to you. We are putting up our best effort to give you everything related to back bonding, so that anything comes in the examination, you just do not do anything wrong. Okay. So this would be trigermyl amine is going to be one exception that you have to remember, where there is going to be a 2p pi 4d pi back bonding, which is an effective one also. Okay. Now let us look at the next donor atom, that is going to be carbon. And the first application, this is the most important application for carbon as the donor atom. This is going to be something that you are going to see repeatedly in organic chemistry. When you're going to start with the study of organic, where you're going to study all the basic principles in general organic chemistry, this is going to be one example that is going to repeatedly come. That's CHCl3. This is more acidic than CF3Y. So in organic chemistry, what you will be studying is, first of all, which is going to be more acidic is going to depend upon whether its conjugate base is more stable or not. CHCl3, on losing a proton, this is going to form CCl3 negative, and CF3 on losing a proton, this is going to become CF3 negative. negative, and these are the two structures that are going to be seen. So we have now an extra lone pair of electrons on this carbon, which is going to make it unstable. Okay. But when we have a carbon with this lone pair attached to fluorines, well, what generally is going to be the answer to the many questions is that fluorine is going to be electron withdrawing because it is highly electronegative. Okay, so what will happen is when it is going to pull the electron pairs toward itself, the electron density on carbon is going to decrease, and hence it is going to make this lone pair of electrons on carbon to be more stable in comparison to chlorine. Okay, so CF3 negative, this should be more stable than CCl3 negative, but what we find is that the opposite is true. Why is it true? Again, this is going to be because of back bonding. Carbon has a lone pair of electron. Chlorine, this has empty 3d orbitals. They can participate in back bonding with each other, and hence the electron density on carbon is going to decrease. Okay, so it is going, this lone pair is now stabilized because of back bonding with chlorine, and hence what we find is that CCl3 negative, this is going to be more stable than CF3 negative. This is one very important application which comes very frequently in the examination. Okay, and this is explained on the basis of back bonding. The next one which you can see is that we have Cr3 negative to be pyramidal in shape, whereas Cn3 negative, this is planar. So again, what you can look is that this is the structure for Cr3 negative. Carbon, this is having a lone pair of electron and it is forming 3 sigma bonds. This is going to be sp3 hybridized carbon. So the shape is going to be a pyramidal one. Whereas in this case, when we have a carbon which is attached to 3 CN groups, when the lone pair of carbon, this gets back bonded to the pi NT bonding orbital of the C triple bonded N group. Okay, so for the cyanide group, this is going to participate in back bonding, and hence we see this to be planar, whereas Cr3 negative, this is pyramidal in shape. So finally, we come up to the last leg of the journey of back bonding. We are going to discuss back bonding with halogens as the donor atom. And the first example we've already done before in the last lecture as well. So it is the Lewis acid order for the boron trihalides. BF3 is going to be the weakest Lewis acid, and the order is going to increase, and Bi3, this is going to be the strongest Lewis acid. I hope you all remember that it is going to be because the Lewis acid character for the boron trihalides, this is going to be inversely proportional to the ability of the back donation by the halogen to the boron atom. And fluorine, this is going to make the strongest back bond. It is going to be far more strong band than with a chlorine or a bromine, and then least is going to be iodine. Why is it so? Well, with increasing size down the group, the mismatch of the overlapping orbital is going to increase. In BF3, it is a 2p pi 2p pi back bond, whereas in Bi3, it is a 2p pi 5p pi back bond. So in BF3, we have the strongest back bonding because of the similarity in the size of the orbitals of boron and fluorine. The strength is going to be more, and because of the electron donation by fluorine to boron, what would we get? The deficiency of the boron atom is going to decrease, and hence it will be having a less tendency to accept electrons from any other Lewis base. So it is going to be having a decreased electron deficiency. So fluorine, this acts as a donor of electrons because it has a filled shell. Chlorine, bromine and iodine, they do not like to donate their electrons. They only do so when the adjacent atom is electron deficient. For example, there is an incomplete octet like the boron atom. Okay, so I hope this is clear. So we are left with just one more example, and then we will be winding up with the lecture. So finally, now the last application, and this is going to be one question for you. Try it and find out the relative stability for the diradicals CF2, CH2 and CCl2. Pause the lecture, try it yourself and then look at the answer. So now if you've done it, let us know. First of all, we will be discussing CH2. In here, what we have is a carbon is forming two sigma bonds with hydrogen. Between carbon and hydrogen, there will be 4 electrons, right? And carbon is also having a lone pair of electrons. So this is meaning that there are going to be 6 electrons for carbon. The octet is not going to be complete. Carbon is going to be electron deficient, and there is no back bonding possible in CH2 because hydrogen, this does not have any lone pair of electrons to share with carbon and decrease its electron deficiency, right? And next, if you look at CF2 and CCl2, both fluorine and chlorine, they will be having lone pair of electrons which they can donate to carbon. So carbon is going to be is making two bonds, so it is going to have empty orbitals, and fluorine and chlorine, then they can donate their lone pair of electrons into that. So we will be having in CF2 a 2p pi 2p pi back bonding, and CCl2 it will be a 2p pi 3p pi back bonding, and this is going to increase the stability of these radicals. Among these two, a 2p pi 2p pi back bond is going to be more stable than a 2p pi 3p pi back bond, and hence CF2, this is going to be the most stable diradical, and hence the order of stability is going to be CH2 is going to be least stable, then CCl2, and then CF2. Understood? Now let us see one more. Well, this is going to be a relation of these two actually. That is why this is just one example. The direction of back bonding is going to be reversed in CCl3 and CCl2. Why? Just think about it. So these are the two structures that we have. We have a CCl3 and we have a CCl2. So here what you can see is now this carbon over here, this is making 3 bonds with the fluorines, and it is having a lone pair of electrons also. Okay. So here the carbon is not electron deficient, its octet is complete. And when its octet is complete, well, now it has chlorine next to it which has empty orbitals, and carbon, this has a lone pair of electrons. So a back bond can be formed between them by the donation from carbon to chlorine. In CCl2 it was a back bond from chlorine to carbon, and in CCl3 it is from carbon to chlorine. Alright, so it is easier for the carbon to exhibit a 2p pi 3d pi back bonding in CCl3 in comparison to CCl2. Okay, so I hope you have understood how the direction of the back bonding is reversed in CCl3 and CCl2.
So that would be all for this lecture as well as this course, and I hope you've enjoyed this course with us. We have tried our level best to give you the best possible education, and I hope you're going to get the best possible ranks in your examination. So we are giving our best wishes for your beautiful future, and we are hoping to be a part of your success journey. So please do join us for more courses and more lectures. Have a nice day. God bless you.